Edward, Ted, you with Ted? Yeah. Owen, Jeremy. Here, you are on the list altogether. I just skipped it the last time, so that's my mistake before. Colin, yep. Matthew Thompson, you go what? Matt or Matthew, right? Yes, either one. Jordan, Jack Walter, Rayanne.
I just go by Ray.
Excuse by Ray. Right. Alex. Yep. And Zachary Wise Copeland. You go by Zach.
Zach, yeah.
Zach. Okay. Great. And Lee is the one that's not. Okay. So, all right, maybe we'll come. Maybe shopping around. So anyway, the homework is posted. It's due on Tuesday. There's some book problems. A couple problems if you do a little bit more. If you're then give a little bit of extra credit for it. I'll give you solutions to those when I post solutions, so you'll see how to do those as part of studying. And there's some practice problems. So you can do those, bring them to office hours, bring them to class on next Tuesday. Generally ask about them. And they might, the answers, there's some answer to some degree in the back of the book. So today what we want to do is talk about probability with equally likely outcomes. So we're going to have kind of a working definition of probability, and with things being equally likely, then it's often a matter of counting the number of situations that occur and are consistent with our events. Right? So if S is our sample space, this is our set of all of our possible outcomes. That we can have from our experiment, and let's say there's maybe n of those overall, and A is some subset of S is going to be the set of outcomes in a particular, that are consistent with event A, with getting a certain state or certain result, getting an income high enough, getting somebody to say yes to a question, or just some numerical outcome that we're interested in. Let's say that there's K objects that are in that. If those outcomes were all equally likely to happen, if all n outcomes are equally likely to happen, then the probability that this event A happens, the probability that we get some outcome consistent with that event, is just going to be the number of objects that are outcomes that are in A that are consistent with our set for our target that we're interested in, divided by the number that are possible, divided by the number of the sample space. And so if these are the numbers over here, so there's just that fraction, right? And one way to think about that is how if you repeated the experiment over and over in time, did it 10 times, 100 times, 1,000, 1,000,000 times, and it was set up the same way every time. We had your full set of objects, and you're going to pick one. Right? What fraction of the time would you actually pick one from that set A that you're interested in? And so sometimes it'd be yes, sometimes it'd be no. Right? But in the long run, the fraction of time that's actually going to happen is going to be equivalent to the fraction in the population or in the sample space there. Right? So for instance, so we're going to explore this with a number of ways. Right? So yeah, we're dealing with probability. If we have a sample space with a bunch of outcomes and they're all equally likely, the chance of some subset of them happening when we pick or do the experiment is just going to be the fraction of times. And so the illustration of that, say they were playing a game of roulette. In the game of roulette, there are 38 spaces. Right? The roulette table has a spinner on it, with a bunch of different spaces on it, and so on. And there's 38 different spaces And that's spinning around, and then they spin a ball, and it goes bouncing around, and eventually lands in one of those spaces. It's supposed to be that all the spaces are equally likely to happen. And so you can play bets. These spaces are numbered 1, 2, 3, up to 36, and then there's another one that's a 0 on there, and there's a double 0 that's on there, and half of these, say the odds in this one are red, and the evens are black. A particular table might use slightly different colors, or maybe switch those, I'm not totally sure. But, and these two have a color of green. So when you spin the wheel, you can place bets on different outcomes. Right? Say, they place a bet on saying, do you think it's going to be red? Right? So what's the probability that an outcome is red? That the ball that goes around and ends up one of these. We can make one of these. Right? We can make one of these red. Right? Sure, these are red. And then there's actually a green one in here. We can use technology to make this more realistic, etc. And then there's others. These other ones are black in there. I won't get into that too much, but in any case, it's like that, and then one of the balls lands on one of those. So, if all these are really equally likely, what's the probability that you get a red? So how many of these numbers, right, would be red? Half of those, just 18. There's 18 numbers here, there's 18 numbers here. So if all 38 are equally likely, right, so the probability of getting red is 18 out of 38. Right. A little bit less than half, right, because it's 18 out of 36 going. What's the probability of getting green? Again, if they're equally likely, there's just 2 green spaces in there, 2 out of 18. What's the different type of bet that you might make? What's the different question you might ask? Yes?
Why is it over 18?
Oh, it should be over 38, yeah. 2 out of 38, out of the whole. Right. I'm just talking and writing at the same time. Right, so you can ask any question you want, right? What's the chance that the numbers come up 1 through 6, right? Well, there's 6 numbers that are consistent with that. If they're equally likely, it's 38. You can ask more complicated question. What's the chance that it comes up on number 36, right? Be 1 out of 38, and so on. So you can ask any number of questions. You could ask, the opposite. What's the chance that it's, the chance that it's green is also the probability that it's not red, right? And not black. So just in ordinary language, sometimes you get opposites or special cases. What's the chance that it is a multiple of 3 and red? And a multiple of 3. How many odds would be multiples of 3? Right? So in this case, we can almost kind of count it out. Right? So not 3, but 6, 9, 12, 15, 18, 21, 24, 27, 30, 31, or 33, and then 36. So it looks like there's 1, 2, 3. Looks like there's 6 of those. Right? 6 out of 38. So sometimes. Is that right? Red and multiples of 3. What am I doing? I'm doing the.
Red is odd.
Red is odd.
So none of those are.
None of those count, right? But multiples of 3. So it would be the other ones, right? I got the wrong. It would be 3, 9, 15, 21, 27, right? 33. Those odds. Those are all odds of the red, and they're multiples of 3. So it should be these ones correspond to that event. Right? Red and even, probably well, in any case, you could, some things would have a, what's the chance of getting a 0 that's red, right? Well, does it ever happen? It's not on the board, it's not possible, so it's 0, right? So, in other circumstances, it's going to be a little bit more involved, so we develop a few rules, right? The first rule or procedure for counting is called the multiplication rule. If you have an event A that's going to happen and event B and something else is going to happen, and ultimately what you're going to observe is the outcome on the first one and the outcome on the second one, right? You could write the result as an ordered pair of the two things that are going to happen. And if the first thing doesn't preclude any of the second ones from happening, if they're kind of independent, not necessarily totally independent decisions in a probabilistic sense, but that they don't restrict each other, right? And there's n ways that this one can happen, and there's a little m ways that this one can happen, right? The number of pairs, number of ordered pairs that you can get, the multiplication rule just says multiply n times n, and you get the number of ways to do this. Right? The number of outcomes that are possible. So our outcomes, right, don't necessarily have to be one thing. It can be a sequence of things, and say, do we get this thing and then this thing? So one place this type of multiplication rule gets used, right? They say you're going to roll two dice, and let's say these are fair dice with, let's say, 5 sides. Everybody does 6 sides, so we'll do 5 sides. I don't know if you could physically construct one exactly like that. Right? And so on the first die, right, you can get the numbers 1, 2, 3, 4, 4 up to 5. On the second one, right, you can also get those numbers. Right? And so if we record what comes on the first one and the second one, we record those two numbers. So how many possible outcomes are there totally? 25. Yeah, 25, right? So the number of pairs is 25. Assuming these are fair, independent die, so you're going to roll them. They're not going to be magnetized or influence each other in some way. And you can distinguish them. Maybe one's red and one's green or something like that. Or you roll one and record it and roll the other one and record it. Right? So there's some physical thing to it. If you take 2 dice that are identical to you and throw them, you can't tell which is which. You can't really put them in order. You just get 2 numbers. So this is putting them in order. Right? So we can ask if all these pairs are equally likely, the probability of getting a particular pair, like a 3 and a 4, is 1 out of 25. So we can ask then question, what's the probability that the sum of these 2 dice is 7? So in these 2 dice, whether it's 5 or 6 or any number of sides, I find it convenient to draw a little picture. 4 lines here, here's 5 separation. Right. And this could be the first die, and it can be the numbers 1, 2, 3, 4, and 5. And then the second one can get the values 1, 2, 3, 4, and 5. And a particular place, like here, corresponds to one of these ordered pairs that we might get. So if that row is 2, and that column is 5, right, we would get those 2 numbers, and that's one that adds up to 7. Right? So this question, this event, that you roll the 2 die and you get something that adds up to 7, right? If they're all equally likely, right, it's an exercise of counting how many ways can you get 7, right, and then dividing by 25. So how many ways can we get 7? Here's one of the ways. This adds up to 7. What else else is going to add up to which ordered pairs are going to give us 7. Right, 4 and 3, 3 and 4, 5 and 2, right? Those are the places that add up to 7, right? So 4 of those, right? So the sum, the probability then would be reported as 4 out of 25, or about 0.16, 16%. 16% chance if you roll these 2 dice, you're going to get a sum of 7. You could do that with any other sum you want, right? What are the possible ranges that we could? So later, we talk about this being a random variable. The sum is a particular random variable. It's going to take on real numbers, right? And we do this experiment, and we translate our outcomes into certain summaries, and a sum in this case. Right? What's the smallest total that we can get?
2.
2. What's the biggest? 10, right? So you could write down 2, 3, 4, 5, 6, 7, 8, 9, 10. This had a probability of 4 out of 25. How many ways can we get 8? Sum of 8. Right?
3 over 25.
Yes, there's 5 and 3, 4 and 4, 5 and 3, and because they're ordered, 5 and 3 and 3 and 5 are considered different outcomes, right? If we're keeping which is first, which is second. Right? So that one's 3 out of 25. Right? There's 2 of these that are 9. Right? So 2 out of 25. There's only one way of getting 10. There's also on the other side just one way of getting 2 as a sum. Right? So what we're putting in the middle here is the sum. So there's 1/25 for that. There's 2/25 for 3, because we need to get a 2 and a 1, or a 1 and a 2. There's no 0, so can't do anything else. And then this one's 3 out of 25, and this is 4 out of 25. The most common is a sum of 6. Right? You can pair any of the numbers with another number and get a 6. So that gets a probability of 5 out of 25. So that's the entire probability distribution for the sum in this case. Right? So these were equally likely pairs. If you're going to roll the 2 die and just report a sum, are those outcomes equally likely? No, these are not equally likely. We would not want to say, well, there's 1, 2, 3, 4, 5, 6, 7, 8, or 9 different outcomes. We would not want to say each of these has a 1/9 probability. Right? It's the process that makes them equally likely. But in this type of case, you could do any other variable you're interested in. Right? You could do what's the probability that the absolute difference is bigger than 2. So, what's the probability that the absolute difference is greater than or equal to 2? Well, there's 25 outcomes, right? How many of them have an absolute difference greater than or equal to 2? Do this quickly again. So 1, 2, 3, 4, 5, 1. So on your homework or on an exam, if there's any type of question, any type of diagram or anything you want to write down, it's fine to do those things. So where is the difference, say, equal to 2 between the first and second? I'll do the absolute value of the difference. So if you get a 1 on the first, you got to get a 3 to get a difference of 2, or bigger, right? So this one works, right? That's a difference of 2. These would be bigger differences. If you get a 2, you have to get at least a 4. Right? You get a 3, you could get a 1, right? Or you could get, the bigger difference up here. You get a 4, there's a couple possibilities. If you roll a 4, you can't get, there's 5, there's no 6 in this imaginary situation. Or these 3. So it looked like if you get any of the pairs corresponding to those places, you get a difference that's bigger. So it's, there's 6 and 6 is 12. So that's 48 out of 100, about 48%. Right, so we're rolling these two, using the simple multiplication to get the 25 possibilities and equally likely, we can answer questions like that. Right? Now, you can go beyond 2. Right? You can do this as many times as you want. Right? So, for example, let's say that let's say I have 4 pairs of shoes. I'm going to work 5 days in a row. 4, 5. And I just randomly pick a pair of shoes. Each day. I'm not concerned about wearing the same one every single day or alternating. I don't not matching it to anything. I'm just randomly picking these. How many different sequences are there? Are possible. Right, if I'm keeping track of the order, which is first, which is second. How would you calculate it? How many choices do you have for the first day? 4. 4 choices, right? So 4 choices. How many choices do you have for the second day? 4. 4 again, right? So on the third day, 4 more choices, 4 more choices, 4 more choices. And so if you multiply all those things together by this multiplication rule, you get 4 to the 5th, which is a pretty big number. It's actually 1,024 sequences. So that would be a lot of different. You could go, for a few years without repeating a particular sequence if you didn't want to repeat sequences, but that's right, that number. What if we can ask probabilities about this question? Right? What is the probability that I get a sequence where one of the pairs of shoes is not used in a particular week? Right? So what probability is that one pair of shoes is not used? All right, now this scenario is a little bit artificial. Saying that I'm just going to randomly pick shoes and I don't have a favorite and I don't coordinate it in any way, right? Right. So, but what's the probability that one pair of shoes is not used in my 5 days? So if all these are equally likely, the chance I choose any one particular sequence, the brown ones, the black ones, the tennis shoes, in a particular order, and then the tennis shoes again, and then whatever, is 1 out of 1,024. How many sequences correspond to this event? We need to count the number of ways of getting a sequence that excludes one of my pairs of shoes.
It's going to be 243 out of 1,024.
So 243. How did you get 243?
3 to the 5th power.
Yeah, that's 3 to the 5th power over 4 to the 5th. Okay, so if I exclude one, I no longer have 4 choices each day. I get 3 choices each day, right? So I guess technically there would be at least one pair of shoes is not used, right? So I pick one pair of shoes and I don't use it, right? Then there's 3 to the 5th. If I wanted to do exactly one pair of shoes that's not selected and the other 3 are, that's a little bit different, right? Because everything would have to come in. But anyway, if I'm just eliminating one, it's lost or thrown away, or not available, then the probability, the other ones are 3 to the 5th, and that gets so it's about a quarter, not quite a quarter, a little bit less than 25% of the time. That would be a 5-day sequence, and one particular one would not get used at all, right? So that's the multiplication rule, going a little bit more for 5 times instead of just 2, and dealing with the circumstances of the question to try and count the number of events, the outcomes that correspond to that one. In general, the general formula, if you are going to do, if you have n objects in your sample space, and you're going to do k selections, and these selections are done with replacement, so that you can pick the same one every time, so the same object can be picked again. Without replacement, we mean we pick it and then not use it again, right? And we are keeping things and keeping track of order. Then there's in the k is the number of possible sequences. And if you can make a case that they're equally likely, right, every sequence, then you could calculate probabilities by figuring out how many sequences correspond to what you're interested in. Right? Not everything's equally likely though, right? So say we have a hockey game. Say we'll have 10 games. And there's 3 different, let's say that we allow 3 different outcomes. Win, tie, or loss. And so we're going to keep track of your season. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to keep track of the 10 games right in there, and whether it's a win, tie, or loss. How many possible game, season sequences can we get out of that?
3 to 6.
Yeah, there'd be 3. Any one of these letters can go. This is n equals 3. The number of games, k equals 10 in this notation, right? And so the number of sequences you can have for the entire season, right, is 3 to the 10. I'll just put it in that context, right? Would all these sequences be equally likely? Probably not, right? Hockey games usually don't split 1/3 win, 1/3 tie, 1/3 loss. Tie, win and lose are much more common. The dominant teams would have a much higher probability of win on any one time, and so we're not going to use equally likely for this one, right? So that would still be it's still true. There's 3 to the 10 possible seasons, which is a pretty big number, but they're not equally likely, right? We will have a formula for calculating the probability of a certain number of wins or a certain sequence coming up here pretty soon, but it's not in this version. Right? But any questions? So this one was done with sampling with replacement, where we can pick the same objects many times over. But in a lot of counting problems or scenarios, we don't reuse things. So sampling without replacement so you don't reuse things. Say you have n objects or people or entities, and you're going to pick k of them and keep them in order. So here's pick number 1, number 2, number 3, pick number k. How many possible different sequences are there for picking k individuals out of the n objects?
Times n minus 1 times n minus 2 until times n minus
Yeah.
k.
Yeah, right, so if you do n choices for the first one, imagine you have n names in a bucket, you pick one out, and you put that one up there, right? So let's say we're at a preschool, all right, and we have 6 kids, right? And we're going to pick 3 to go to the drinking fountain. Right. Next, we can go in the second shift to go to the drinking fountain, right? But one teacher or teacher's helper will take the 3 kids there, and we're going to put them in order, right? How many sequences are we can pick any of the 6 kids to go first? But once we pick that particular child, they're not available anymore. We're going to pick a different one, right? So there's 5, and then 4, and similarly, if we have picked n on the choices from the first, and then we hold that one out and have to pick from the remaining, it's n minus 1, and then n minus 2, and then it goes down a certain distance. N minus k, is it n minus k?
Plus 1.
Right. It's going to be n minus k plus 1, actually. Right. And so if n is, yes?
Since you're picking 3 kids, it would be like 6 and 3.
Will be 6, then 5, then 4. So we have 6, and we multiply these together. Right? So imagine their first names begin with, you know, A, B, C, D, E, and F, right? Whatever they are. Right? So Alice and Bobby, yes, and so on, and Frank, and you know, right? And you can pick them, right? So you have to put somebody's initial there. So first you pick person A, right? And then you got to pick another person out of the ones that are left, so you get 5 choices. Right? Maybe F, and that would be one sequence. Right? These 3 were picked to go in the first group going to the water fountain. A, Allison gets to go first, then you know Don, and then Frank, or whatever their names are, get to go and drink at the fountain, right? And how many ways can that happen? It's very important to keep things fair and balanced, right? Or at least the perception of it for some groups, right? So this would be, you know, 120 sequences of 3 children. So if n is 6 and k is 3, right? N minus k plus 1, right, is this last number, is 4. Right? If you put everything in order, right, put them all in order, it's called a factorial. So if you have n objects or children, put them in a particular order. Another way of saying it is that you pick n of them, you pick them all without replacement. And then one and the next one until you exhaust all the choices. Right? The number of ways of getting these sequences of length n is n times n minus 1 times n minus 2, right, all the way down until you have your last person there. And that's just 1 times. And that's called n factorial for shorthand. Right. Instead of writing that in a lot of different formulas and situations, just mathematically, that's just there, right? So if you want to put all the 6 kids in order, line them up to walk to the playground, take them all. How many different orders are there? Right? So that's the answer to that would be 6 factorial, right? 6 times 5 times 4 times 3 times 2 times 1 ends up being 720 sequences. We could ask probability questions about this, right? Say, if all the sequences are equally likely, right, then the probability of one particular sequence, right, probability of the sequence A, B, C, D, E, F, is just going to be 1 out of 720. If that sequence is just as likely as any of the others. Right? Now, what if A and B are girls and C, D, E, and F are boys? Right. What's the probability that the girls come first and the boys come second? So the two girls are there at the beginning, and then the boys come next. All right, so we have to count, figure out how many ways can that actually happen when we're randomly assigning. If all these sequences are equally likely, so that, if we believe that, there's not one child who always clamors to be first or something. Right, we need to know how many ways that happen. Any ideas about figuring out that way? Yes.
You have to account there's like only 2 options for the first and then for 1 option for the second, and there's 4, 3, 2, 1.
Yes, right. So we have to put in these 6 spots, right? The way we set it up puts a division, but there's the 2 girls, right? So you have to choose one of the girls, and then the other one has to go there. Right? But for the boys, starting in that second portion, right? You go 4, 3, 2, 1, right? And choosing the girls is done independently of choosing the boys. So that's the multiplication rule, right? So there's 2 choices over here. 4 times 3 times 3 times 1 is 24. So you multiply those together and you get 48. What's the probability that the boys come first and the girls come second? Yes.
48.
It's also 48, right? We're just kind of reversing it, right? You get 4, 3, 2, 1 choices for the boys, and then 2, 1 choices for the girls, and multiply those together, right? So the probability of the boys come first, and the girls are second, right, is also going to be 48 out of 720. So what's the probability that the boys and girls are separated in the line? Either one of these scenarios works, right?
96.
96 out of the 720, right? So if the event, the outcome we're interested in can be satisfied one way or the other, we can add those together. In this case, there's no overlap between those 2. Right? So the probability, right, the girls and boys grouped together in line. There's 48 one way and 48 the other way out of the 720, so 96 out of 720. So some of the probability calculations try to do more kind of involved things like that, where you figure out that there's this one way and you count that, and other ways can happen and count that and add them together. So one thing that I think some people find frustrating or challenging about probability is reading the problem and figuring out, is it without replacement, with replacement, are you putting everybody in there or not? And some of it takes experience, and some of it takes just kind of relating what you see in this question to other examples that might be similar. So it does take some practice. That's why there's some practice problems as well as some other ones. So, have you heard of this birthday problem? Let's say you have K people, and what's the probability that there is a duplicate birthday in the group? about that, we need to simplify it a little bit, right? We can say that we're going to take 365 days. Is anybody born on February 29th? Every once in a while, you put somebody is, right? But let's just take the other 365 days, right? Let's assume that the days are equally likely. Days are not equally likely in the population. There's some seasonal variation that actually exists, but it's close to kind of first order approximation. Right? And let's say that there's nobody in here appears to be a twin or related by name, right? So no twins. So everybody's birthday is independent of one another. They're not related in some way, right? So let's make it concrete. Let's say that, maybe there's 15 people. That's about half. Meaning we have in our class, what's the chance that somebody in this room has a duplicate birthday? Right? Oh no, that's my other class. This class is more like 22. Right? And what's the chance that somebody in this room has the same birthday as somebody else? Right? So if we don't have duplicate birthdays, how many different sets of birthdays can we have? This problem, you can think about the denominator and the numerator as separate things. So for 22 people, how many different sets of birthdays can we have? Yes?
365 times 22.
Yeah, we're raised to the 22. Right, yeah. So 365, there's a lot of them, right? Raised to the 22nd power, right? There's a first birthday, and a second birthday, and a third birthday. And like with two people, it'll be 365 times 265 for the choices, right? Now, so that would be the sequences for all 22 people with no restrictions, right? And that would be the total. That's a lot of different possibilities, right? So duplicate birthdays. How many ways can we get duplicate birthdays? That's actually hard to count directly, right? Because you two could have the same birthday, or you two could have the same birthday, or three people could have the same birthday, right? And there's just a lot of different ways that can happen. Right? What's easier than counting the duplicates? Right?
Unique. Everyone has a unique.
You can take 1 minus, right? You can take the opposite. The opposite of some duplicate is all different, right? So you can do 1 minus the probability of no duplicates. So no duplicates means all different birthdays. And sometimes these probability problems, you have to rephrase it to make it kind of gel that, oh, that's a way of looking at it. So again, there's 365 to the 22nd terms in the denominator. Now we can count how many ways there are of taking 22 people and giving each one a different birthday. Or having a set of 365 birthdays and picking 22 different ones. Right? This one was with replacement. If they're all different. Now that's without replacement. I think this problem, besides being kind of, it's about birthdays, if you think about it in terms of themselves, contrast these two ways of counting. Right? So for the first person, right, the first person can choose whatever, right, 365. How many choices are there for the second person?
364.
364, right, if we don't match. Right? And I'm just going to put little brackets here, and I need still multiplication there. Right? So the next person is 363, right? And this keeps going down until we have everybody in there. How far do we go down? And this formula, that's if you go all the way down. we're only gonna go down a certain distance, so it's this version of things, right? 365 days, 22 people, plus 1,
334.
334. There it is, 334, the last thing multiplied. So 365 minus 22 plus 1 would be 363, but plus 1 is 334. All right. So if you multiply all those, how big is that probability? I couldn't judge this one by myself, right? We will, one thing we'll do with computing eventually is this R statistical package. We'll come back to, I wrote a note to myself to start that, but I didn't yet. Let's just take a moment to start. Do you have any sense, it was 22 people, what's the probability that we have a duplicate? 22 out of 365, it doesn't seem very big, does it?
But you're multiplying together the biggest numbers of the bunch.
Yeah. Yeah, those are the biggest numbers, right? So 1 minus, so k, if we can do, say, the numbers through 30. When you get a homework or something like that, you'll get some sample code and things like that. But you can make a vector of this number here, right? So our probability, and that little backward arrow means a sign, like save that number in there. Well, we wanted, there's a product command. So 365, you can go downwards too, right? 365 minus k plus 1, right? We want the product of that. And the denominator is the product of, it's like 365 raised to the kth power. Right? Product of those. Oh, it's a little bit harder to do. So the probability, well, let's see. I'll just do the 1. Okay, so k, oops, what I want. So the product, that's going to be for 1k. So we want 1 minus the product, say, of the 365 down to the 334 is R1, and then the 365 raised to the 22nd power. Right? Who thinks this is going to be less than 1/2? Bigger than 1/2? You think it's going to be small? Right. But it ends up, oops, that's not good, right? The product of these, what am I doing? 365 to 364, 365 raised to the, this is supposed to be, no, that's not what it's supposed to be. The product of, and I think it might be having a problem here. Let's do it a different, I don't know what's going on exactly. The sequence from 365 down to 334.
I think it's 344.
344. That would do it, right? So let's go back up here. Where am I? 344. So it's about 47%. It's pretty near equal, right? So actually, if we had one more person, this would go down one more, and this would go like this. It would be slightly over 50%. So there's a chance that we've got a 50, even chance almost that there's somebody in this room has a duplicate birthday. Are you interested in finding out?
Yes.
Yes. All right. So if you wouldn't mind, we'll just go through and say your birthday. So when's your birthday?
October 3rd.
October 3rd. And if somebody has a duplicate, just speak up and say, I match somebody. So October 3rd, what's your birthday? March 3rd?
December 19th.
October 22nd.
June 10th.
October 31.
January 26th.
October 7th.
April 22nd.
April 10.
January 26th.
January 26th. So that's a duplicate, huh? Yeah, okay, we got one.
February 4.
February 4.
June 26th.
October 20th.
September 18th.
April 28th.
October 13th.
January 10th.
July 22nd, September 12th.
Yeah.
On July 7th.
So,
January 31st.
January 27th.
so,
July 30th.
by 30th. So we had one duplicate, right? We had a 50-50 chance about, and so it worked out. So, right, great. And so it grows pretty fast, right? If there's just two people, right, then it would just be 364 out of 365. It's almost certain that you don't match. It's very, and the probability that you don't match is quite high. So there's a very small probability. 1 out of 365. One person has a birthday, you have to pick somebody else, you have to pick that 1 out of 365. So that's pretty small. But once you get 2, 3, 4, there's many different ways that you can get a match, right, with the people. So it takes off. Where towards the end, if you have 100 people, 200 people, you're almost surely going to have it, even though it's about half the birthdays. Okay. So, we've had this multiplication rule. It's equally likely events. We can try to count things there. Sampling without replacement, or if it's without replacement, or the factorials. There's another one where we are counting, where we have n objects, and we pick k of them. But order doesn't matter. Occasionally, it's more convenient to count, not keeping track of order, but just keeping track of the set of things there. So this is sampling without replacement, like the other one. And then the results are unordered. And so, say you have, 6 of the children. A, B, C, D, E, and F is representing the names. Right? You want to pick 2 of them. Pick 2 helpers. There's not really a first helper and a second helper. You just need 2 of them. Right, so picking A and B is the same as picking B and A. Right, how many ways to pick? So if you did keep track of order, right, how many ways would there be to pick 2 children? The first child and the second child?
6 squared.
If you could pick them the same, that would be with replacement. Right?
Wow.
Right. So you could, if you picked, and you're asking questions, and there's 6 children, and you pick A, and that person, or pick person D, and they ask a question. With replacement, you pick them to answer a second question, and you pick that person again. So if it's with replacement, it's 36. Right. 6 choices for the first one, 6 for the second. But if you're going to pick the 2 people and not let them repeat, right? Then there's 6 times 5, right, without replacement. That's with replacement. But you could pick person D and then person E. You could also pick person E and person D, right? We don't really care which, if we're just, here's our 2 people, we don't care which was first and which is second. They both are going to do the job, right? So this is replacement with order. So how many ways are there to undo this order? How much duplication and counting do we actually get by saying, if we said there was 30? So for each, A, B, B, A, or D, E, E, D, right, there's a double. Right? So we really need to divide that by 2 to get 15. Right? And we can actually list it for this. 15 is about that. Right? So we could do A and B, A and C, A and D, A and E, A and F for 6, right? And then but our first one could be B. But we don't want to count B and A again, right? So B and C, B and D, B and E, B and F. We don't, and we have to start with a C, we don't want to do AC or AB, or BC, sorry, AC or BC. We don't want to put A or B there because that would be redundant to that. So CD, CE, CF, and D, again, we don't want to do any of those three, so DE, DF, and that only leaves E with F. E is with all the other combinations before, and that's our 15 possibilities. Right? So we don't care about order, and we use things based on order. There's this overcounting, and we want to adjust for that. And so this is called a combination. Is if we have n objects and we pick them, right, there's n times n minus 1 times n minus 2, and all the way down to n minus k plus 1 choices. Right? But these unique items, we could mix up the order and we'd still have the same set, like a hand of poker, like a hand of cards or something. Right? So how many ways can we reorder them and still have the same equivalent set? Yeah, there's a k choices. In any one of the k objects could be first, right? Like either of these children, A or B or A could be first, right? We reverse it, we get the same one. But if there's k of them, we could do k minus 1, k minus 2, right, all the way down to 1. Right? We pick k, and we put k in order, and that's one particular sequence. And so this is going to be our answer. Now, this can also be presented as, is presented another way, where you take that thing on top and imagine putting all of the elements in order, right? Going n times n minus 1 times n minus 2, right, all the way down to 1. Put them all in order, right? And then the ones you keep are the first k. Right? If you put them all the way down, then you could reshuffle the ones you keep. You could also reshuffle the ones you don't keep, and everything would still be the same. You'd still have this first k objects would be the same individuals. So you could reshuffle k minus k, k minus 1, k minus 2, all the way down to 1. But you can also reshuffle the ones that come later in the sequence that you're not going to keep. And then how many of those are there? There's n minus k of those. There's k over here, there's n minus k that come later. You could reshuffle those, n minus k minus 1, all the way down to 1. And so this can get written as n factorial, which is n all the way down, divided by k factorial, taking your k that you've chosen and reordering them all the way down, and then n minus k factorial. And this combination thing is given another special symbol, n k, with the brackets around it. And sometimes it's called n choose k, the number way of choosing k objects out of n. And so that is presented as the way of choosing k objects out of n, where you pick without replacement, no duplicates, right? And you don't care about order, you just care what set you have there. Okay. So in this children's example, we have 6 children. You pick 2, that's k, and how many sets of children are possible? Well, the answer is 6 choose 2. We've reasoned it as there's 6 for the first choice, 5 for the second, but any particular sequence we have, we could have reversed it. A, B, B, A gives us the same 2 children. We divide it by 2 times 1, so we get 15. Right, in the other notation, it's 6 factorial over 2 factorial divided by 4 factorial. So in that later version, you imagine you pick somebody for the first, and you pick somebody for the second, and then you put everybody else down, A, C, D, right, and F down there. And these are the two you're going to keep. These two, these are you're not going to keep, but you imagine you just line them up anyway. Right? Maybe the children just get up and stand in a line. It's kind of random in case. But so you keep these, so you could reorder these two, but you would also get the same pair in your keep pile if you reordered these. So if you took 6 factorial all the way down, there's a lot of duplicate counting, and you adjusted that by dividing by this. So what does this thing mean? Right, 6 times 5 times 4 times 3 times 2 times 1, and this one is 2 times 1, and this is 4 times 3 times 2 times 1 factorial, and the last bit of this sequence always cancels. So it's our 15 sets. Right. So one other example with this, let's say you have 100 items and you're going to inspect 4. How many ways are there to choose 4 for inspection? How many sets of 4 can be chosen for inspection? How would we compute that?
Factorial over 4 factorial times 96 factorial.
Right, so this symbol can be written as 100 over choose 4. Right, so 100 choose 4. And so often it's presented as 100 factorial over 4 factorial, 96 factorial. Right? But for practical purposes, the 96 factorial is going to cancel with all the 96 factorial going all the way down, so you don't actually want to write out or tell the computer to actually calculate that many numbers. Computers actually would start to get numerical overflow that it gets too big to store in memory. 100 factorial, 1000 factorial is ridiculously large. Right? So you can just take the first 4 numbers up here, right, and the first 4 numbers down here. If this had gone all the way down, it would begin with 96 and go down. But that 96 factorials would cancel. Right? So there's a 96 factorial left over here, and those 2 things will cancel, so you don't need to do them. Right? So it's more manageable that way. This still ends up being 3,921,225. When you're picking from 100, there's a lot of ways to pick 4 different objects, right, without replacement. Let's say that it's phrased differently. Put 96 in a box for shipping. Inspect the others. So how many ways are there of picking 96 objects out of 100 to put in a box? I'm not being careful about, how I put them in the box. Just put it in there, right? I don't care what the order is.
100 choose 96.
Yeah, 100 choose 96. Is that difficult to calculate?
It's a lot bigger.
It's a lot bigger. Well, those 2 numbers are a lot bigger, but there's a shortcut, right? If you pick 96, you leave 4 out, right? And if you pick 4, right, then you leave the other 90. If you take out 94, then the other 96 are left, right? So this would be 100 factorial over 96 factorial, and then 100 minus that is 4 factorial. Right? But it's equivalent to this one. Right? So picking 4 and leaving out 96 should be the same as leaving out 96 and picking 4. Either way, you prefer view it. Right? So this is 100 factorial over the given multiplication is commutative, so you can reverse that. So that's the same as 100 choose 4. And so whichever number is smaller, k or n minus k, you can do that calculation, right? And you don't have to do the bigger one. So this is the same number as this. But phrasing it as pick 96 out of 100 makes it sound like you're doing a lot more work. Taking the 4 out for inspection and then putting the rest away is probably how it would be done anyway. But counting, it's easier to do that, right? So with the children, 6 choose 2 is equivalent to 6 choose 4. And you can do whichever one is easier, right? You really only can do this one. So 6 times 5 over 2 times 1. There'd be a 4 factorial continuing down, but it's 15. So when computing those, particularly by hand or on a, it's easier to do, realize that kind of opposite property for the calculations. So let's say we have an example. Let's say we have a population that has 1,000 people in it. Let's say we're going to pick 3 of them. Right. What's the probability? What's the probability that a particular person is in the sample? So in the sample, we don't care who's first or second or anything. It's unordered. We just get this set of people, right? And we're going to pick without replacement, right? So unordered without replacement. So if this is simple random sampling and all our samples are equally likely, how many possible samples are there? Thousand people in the population. You're going to randomly pick 3.
1,000 choose 3.
Yeah, 1,000 choose 3. 1,000 choose 3. So 1,000 times 999 times 998 over 3 times 2 times 1. Right? That's going to be our denominator. Now we're interested in a particular person. What's the chance of the person? We have 1,000 students. We're going to pick 3 for some question and answer period or something. And what's the chance that the student with the first name in the alphabet, right, ends up in the sample? Right, that particular person. So let's assume all samples are equally likely, right? This is really, all the names, we're drawing them out of a hat, it's all fair and balanced, and all the samples are equally likely. How many different samples would have that particular person in there?
Would it
Yes.
just be like how we had been setting it up before with the 3 spaces, like 1 and then 999 and then times 998?
Yeah, it's related to that, right? So that's a good way to think about it. We have our 3 spaces, right? And here's the person's initials, AA. That's it. That person's in the sample. Now you need to pick, you gotta complete the sample. Right? So how many ways can you fill in that? Right, there's 999 people still left. Do you want to do 999 times 998? Right, we don't really care what the order is of these samples. Right? We have this person, right? So we want to actually do it without replacement. Yeah. So the number of ways of completing it is 999, choose 2. Right? So again, we don't care. Or 2 times 1. This is the number of samples, including that first person. So if you pull one out, there's 990 people left in the population. You still got to pick 2. Right? So 999, choose 2. And this doesn't end up being too bad to do. So there's 999, 998 over 2 times 1. And this is what we had before, 1,000, 999, 998 over 3 times 2 times 1. That's all in the denominator, that's all in the numerator. So we get some cancellation. Right? The 999, 998 cancels with what's below. The 2 times 1, 2 cancels. It leaves 1,000 in the denominator. And that 3 that's in the denominator flips over. Right? And becomes down here. So the probability of a particular person, any particular person you want, is in the sample is 3 out of 1,000. Kind of makes sense, you know, intuitive that there's picking 3 out of 1,000. The chance that you're in there is 3 out of 1,000. But actually to show it and justify it, besides saying, well, it seems to make sense, that would be a reasonable chance. We've counted the number of samples that are possible. And assuming they're equally likely, we've counted the number of samples that include one particular person. Right? And taking that ratio, use that equally likely principle to count it. But any questions? In the general case, in survey sampling, which is a field of statistics, the number in the population is often given as capital N, and the sample size is often given as little n. Right? In our book, we use different notation. Right? So the probability. So in a simple random sample, all samples of size n, little n, are equally likely. The probability a person is in the sample is now in the denominator we have capital N choose little n. Kind of replacing our little n and k by this different notation. I'm only doing this because in survey sampling, if you read any books, it typically uses that notation. And then if we have that one person and have to fill out the rest of the sample, well, there's capital N minus 1 in the population left over, and we have to pick little n minus 1 of them. And if you do a little algebra or write things out, it ends up being little n over big N, or the sample size over the population size. So the probability somebody's in the sample in a simple random sample is just the sampling fraction, which is, you did that example with the 1,003, and it came out to work out that way. But it works out in general. Right? You have to use symbols to do that, but we'll do more with symbols and formulas on Tuesday. Right? We'll return to using more the algebra approach. Most of the first homework is more applied, just an example. There's certain things you can prove, the different relationships you can prove about these different symbols that are useful to know at certain times. The first homework is more practical in terms of applied problems. Sometimes makes it harder, you know, figuring out what context and how to view a problem, right? But any questions about? So that's essentially the material that we need to do the homework, so I thought we'd look at some other problems. But is there anything that strikes you as particularly hard or confusing, or might be hard to express what that is? And maybe from looking at some others, we'll see some of these, right? So in R, for example, just to, right, when we do this, once we get into some computations, there's actually this function called choose. There's special math functions for different things. And this choose is a function here that will give you the number of ways of choosing k objects out of n. And there's a little explanation there. Where is it there? Choose. These are called binomial coefficients, and it defines what it is there. These help functions, so look, there's a choose 5, choose 2. You can kind of cut and paste that thing in there. Or choose a number of 10, right? So 5 times 4 divided by, 2 times 1 is our 10 numbers. So our choose 100, 1,000, choosing 3 is this huge number of surveys that are possible if we need to choose 999 with 2, right? That ends up being that number, and I just pressing the arrow keys can help you go up and down through those, so it can save you some typing. Choose 3, and that's 0.00, which is 3 out of 1,000. Right? So this choose mathematical function is built into the program, and so for some things that can make computations. You don't necessarily need to use this at all for any of the homework. There are problems that you can do based on just the smaller numbers and doing it by hand with a simple calculator. Some calculators might have a combinatorics and choose k built into it as well. Right? So let's look at some examples. Right? Right. So let's say you have there's 3 races. Right? And in each race, there's going to be 8 horses. And you pick a horse in each race. And you don't know anything in particular about these horses. You're just randomly picking the numbers, right? Random picking. What's the number of selections that you can do? Yeah, 8 cubed, right? So you have your three races, you get 8 choices here, 8 choices for the next one, right? So 8 cubed, which is 512 possible different alternatives. Now a trifecta, I don't know, let's say what a trifecta is, but say you, what's the probability of picking the winner in 3 races? Right. To answer that, right, well, let's assume, not very realistically, that there's equal chances for all horses. So that any of our 512 sequences is equally likely. That's not realistic, right? Because there'd be favorites and odds and things like that. We'll probably deal things with more realistic odds and different things. Right? What's the chance you win pick the winner in all 3 races? Yeah, there's only one way to do that. You got to pick the right one, that one, right one there. So just 1 out of 512, right? Or less than about 0.2%. Right? What's the chance that you pick the winner in at least? You pick the winner in 2 races. exactly 2 races. It's a little bit more involved to count, right?
We just figure out how easy it is to pick one winner and then one minus.
So yeah, I mean, it's good. It's always good to think about that type of thing. Like sometimes the opposites, right? But if it's, you know, the opposite of all 3 races, we'd be picking, you know, 0, 1, or 2. Right? So it would include 0, 1, or 2 correct picks. Right? So that's a little bit bigger than this one is. But so since there's 3, you got to, you know, win in 2 of these races. So let's say you have the winner in these 2 races. How many ways are there of picking the horse that did not win in that 3rd race? 7, right? So there's 7 picks here. But that would be the scenario if you picked the winner, and then missed. We could have a different pattern. We could have win, and then miss, and then win. Right? So we could do win, and then an incorrect one, and then a win, or we could miss the first one and then pick 2 winners afterward. And I think that's all the ways that we can pick. Right? So of course, it's 1 times 1 times 1. 1 times 1 times 7 is 7 in this case. So there's 7 in each of these scenarios. They're all distinct, right? Because it's not the same pattern. Right? No way that you could overlap. So
21.
21, right? 21 out of 512, you get exactly there, right? So sometimes probability says, well, you know, we have to pick 2 winners and this, right? So there's 7 this way. But how many ways were there of choosing 2 winners? Right? 3 choose 2 is 3 times 2, or 2 times 1, or just 3. Right? So some problems get broken into, you pick the places to be winners, and then you pick the other ones. Right? And that kind of determines it, so kind of in stages for more involved problems. Right? Okay. Maybe we'll do one other kind of like that. We just kind of, any questions about that one? So 21 out of 512 is completely random, and there's really no advantage of any horse that you would get these 2 winners. A second problem here, so the game of solitaire in cards, right? The card game. A standard deck has 52 cards. The cards each have a suit and a value. So there's 4 possible suits and 13 values. And 4 times the 13 is the 52 cards. So the 4 suits are, you know, club, diamond, right, a heart, and spade. And then the 13 values go 2, 3, up to 9 and 10. And then there's a jack, queen, king, and ace. So there's 4 of each of these values. The book uses a few examples for poker or dealing cards as well. But this is the setup that they're doing. In solitaire, you put a card here, and then you put 2 cards here, and then 3, and it goes out to 7. 3, 4, 5, 6, 7. So there's 5 here and 6. 5, 6, 7. 1, 2, 3, 4, 5, 7, 1, 2. Right. So it sets up like this, and you see just the top cards. You see these top ones. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. Right. So 1, 2, 3. Yeah, 7. Right. So you just see the top cards. The other ones are down. And if you get to do something, if you're allowed to move this one, then you turn over the next one. Right? So that's how the game is set up. Right? So you deal these all down to set up the game. Right? What's the probability that a probability related to this is that there is no ace showing right at the start. So we deal it all out. We don't know any what's down there. We don't know what's in the rest of the hand, the leftovers that's going to be used later. We see these 7 cards out there. What's the probability that there's no ace showing? What are some ideas for it? Yes?
Would be 52. There are only 7 spots that it could be showing.
Yeah. Yeah. So there's 7 shots that are showing, so we need to put 7 cards there. Right? So that's going to be our denominator, right? 52 choose 7. That's the way of dealing it out and having 7 cards showing, right? So any 7 cards showing their face. Their faces. Their faces or their, so we know what their suit and sorry, I'm getting a little messy, rush through. Now, right, assuming those are all equally likely, it's well shuffled, it's been dealt fair, right? What's the chance that there's no ace showing in those 7?
There are 4 aces, so is it 48 choose 7 as the numerator?
Yeah, so that'd be 48 choose 7, right? Having no ace in here, we've taken that out. Right. And so the other ones then can be shown. And there's some cancellation in there. Do I know what that is? This is about 55% once you calculate those couple of things. If you do it by hand, it's 48, 47 down to 42, and then 7 factorial in the denominator. There's a 7 factorial in the base of this one too, so there's a cancellation. What's the chance that there's 1 ace showing? So the denominator can be the same, 52, 7. One way to do this might be convenient to think about choosing in 2 steps. Right? You have to choose 1 ace, right? How many ways are there choosing an ace? 4, right? So you choose 4, choose 1. Right? And then you have to choose the others. How many are left in the population of cards, right, excluding those aces?
You have 48.
There's 48 there, right? And how many more cards do you need to choose to get your face-up cards?
6.
Yeah, 6, right? So I don't have that one calculated. All right. One quick last problem. Right. So you have 6 math majors, 7 CS majors, and 5 biology majors. And you need to pick 4 4 individuals to make up a team. So this is 18 individuals overall. What's the chance that, what's the probability that one group is not included? Or
Downstairs is 18, pick 4.
yeah, the denominator can be 18, pick 4, right? 18 people, you have to pick 4.
And so the top can be 3 different things plus like 12 pick 4 and 11 pick 4 and 13 pick 4.
Yeah, so we have to break it into, this one's a little bit more involved, but there's 3 parts here, right? 3 different ways of satisfying one group is not included, right? So you leave out the math majors, right? You're left with 12 people. So 12 choose 4. So this is leave out math. If you leave out the CS majors, you have to choose 4 from the other 11. So 11 choose 4. So I guess this is really at least one group, right? Because I'm not guaranteeing that I get some from the other 2. I mean, it could be that I only pick math, but then at least one group is left out. So it's, right. Or if you leave out biology, then there's 13 people, right? So you'd have to go through the process of.
So like if you want to go like one group is not select, you can just cancel the like only choose one group like 7 pick
Yeah.
4 or 5 pick 4. Like
Yeah,
this.
right. So the book mentions something called an exclusion. So sometimes you count something that's a little bit bigger, and the thing that we could select or subtract is the number of ways that you get only one group. Right? So 6 choose 4, plus 7 choose 4, plus 5 choose 4, we use the number of ways of only getting math, only getting CS. If you subtracted that out, then it would get down to exactly 2. Okay. So the problem set had to do a few problems, and so look at it from different ways, contrast it to other problems, and numerical calculations aren't as challenging. It's figuring out how it fits into the story context. That kind of look at it in 2 different ways if you can and try and deal with that stuff. So I'll have office hours tomorrow and Monday, so we'll have a little time to talk about it
Remind me what you're on to.
You have to You have one class today? Or
No, I got up
something?
at
Yeah.
Well, so, I just have a symmetrical schedule that I have 2 classes a day. Thank you. See you on Monday. So like it means that it seems like I have a lot of time, but I also have to go to class every day.
Yeah, well, so do I.
I don't have a day like technically that's entirely empty or almost entirely.
Thank you. I'm not either.
Oh, cool. Have a good one. Have a nice day. Yeah, no,
Thank you.
I was gonna try to.
Thank you.
Yeah. Hey.